Hello and welcome to my YouTube channel. Today I'll be solving last year final examination on applied electricity. This is our examination for 2024-2025 academic year. So I will start right from question 31, right? Question 31. A conductor of length 1 meter carries a current of 800 amps at 30 degrees to a magnetic field having a flux density of 0.5 Tesla. Calculate the force on the conductor. So the force, we use this formula. Force will be equals to magnetic field strength times the current times the length of the conductor times sine of the angle between the magnetic field and the conductor. And that is given as 30. So we just write here. The magnetic flux is given as 0.5. The current 800. Then the length, which is 1 meter. So times 1 times sine of the angle, that is 30 degrees. So we have this. So sine 30 is 0.5. So 0.5 times 0.5, that will be 1 over 4, right? 1 over 4 times 800, you get 400. Right? You get here 400. So the answer here will be what? B, right? So yeah, you get not 400, 200 rather. 800, 8 by 4, that will be 2. So you get 200. 200. Get here to be 200, which is C. So the answer here is C. A magnetic field strength of 2000 amps per meter is applied to a circular magnetic circuit of mean diameter 150 millimeters. If the coil has 600 turns, find the current in the coil. So here you can see we are given the magnetic field strength, we are given the length, we are interested in the what? The number, we are interested in the current. So we know for FM, right? The formula is current times the number of turns, or there's also another formula for the MMF, the magnetization force or the magnetomotive force, which is also equals HL, right? Yeah, we are interested in the what? The current. So we combine this, we make current the subject, that will be equals to what? HL means the magnetic field strength and the length of the conductor over the, right, times the magnetic flux path over the number of turns. We have this formula, we just do replacement. Then we have been told this is what? A circular magnetic circuit. What that means is that the length, since it's circular, the length of the magnetic flux path is going to be equals to what? Pi d, meaning the circumference of the circle, which is pi d. So we have h, right? So we have this. We can start doing replacement. The magnetic field strength is given as 2000 times the length, that will be pi, times what? D, the diameter, which is what? 150 millimeters, all over the number of turns, 600. So when you solve this, the answer here is going to be D. You get the answer to 1.57 amps. Find the relative permeability of a piece of silicon ion if the flux density of 1.2 Tesla is produced by a magnetic field strength of 600. Here we are interested in the relative permeability. We know that absolute permeability of a material, in this case silicon ion, that is silicon ion, will be equals to the magnetic flux density over what? The magnetic field strength. And absolute permeability of silicon ion is also equals to what? The relative permeability of silicon ion times the relative permeability of silicon ion times the permeability of free space. That will be equals what? Magnetic flux density over the magnetic field strength. So we are interested in the relative permeability of silicon ion. So that is the equals to, we make it the subject. Silicon ion. That will be, this abbreviation is for silicon ion. That will be magnetic flux density over here. The ability of free space times the magnetic field strength. This we get, replace the values. Magnetic flux density is giving us 1.2 over the permeability of free space, which is 4 pi times 10 to the power minus 7 times the magnetic field strength, which is 600, right? So we try and then we do this, you get the answer here to be equals to A, which is 269.8 amps per meter. So the answer here is A from this. Moving on to the next question, 35. Determine the magnetization force required to produce the flux density of 1.3 Tesla, right? So this is a preamble question. No, not that one. We are not. So this is what's this is not the answer. When you do this, you get this rather. You get D here. So you calculate, you get D, which is going to be equals to this, right? Okay. Okay. So here the answer is going to be D, which is 1,501.55, right? That is if you take the relative permeability of silicon ion is equals to magnetic flux density over permeability of future times the what? The magnetic field strength. So we have 1.2 over 4 pi times 10 to the power minus 7 times 600, right? The answer here is 600. You get 1591.55. So the answer is D. Find the magnetic preamble 2. You have to use this preamble to solve question 34 and then 35. So we have this here. Find the magnetic field strength needed to produce a flux of 1.3 Tesla. Again, so here too, the formula again, we know that relative absolute permeability of cast steel will be equals to what? The relative permeability of cast steel times the permeability of free space of cast steel, mean the permeability of free space, which will be equals magnetic flux density over the magnetic field strength. We are interested in the magnetic field strength, so we make it the subject. We have this, all right? Absolute permeability, magnetic flux density over absolute permeability of cast steel. Yes. That is going to be equals to magnetic flux density is giving us 1.3 Tesla over the permeability of free space 4 pi times 10 to the power minus 7 times 5,000. That is the relative permeability of the cast steel. So again, you do this calculation, you get the magnetic field strength to be equal to 206.9 amps per meter. That will be A, right? Moving on to question. Okay, we move on to question 35. Determine the magnetization force required to produce a flash density of 1.3 Tesla. So here we are interested in the magnetization force, which is Fm, right? The mmf. You know, Fm is equals to Fm equals to HL, mean the magnetic field strength times the length of the magnetic flux path, and that is given in the question as 20 millimeters. So we have this times 206.9 times 20 millimeters. And what do I get? So its answer here should be equals to 206.9 times 20. So we have this, and it's milli, right? So that will give us, so we have this 4138 times h power minus 3. That'll be 4.14 amps. So the answer here will be B. Move on to the next question, and we have a preamble again. But this time the preamble we have to use what? Figure 1 on page, right? So I think here is a mistake. This is not figure 1, right? But this figure is on page 11, right? So we go to page 11. Page 11, we know we are going to re-get it later, right? So we are in 30. So we are in 36. So this is what? First, let's check the material is mass steel. Have mass. A mass steel ring having a cross-sectional area of 500 millimeters square and a mean circumference of 400 millimeters has a coil of 200 turns wound uniformly around it. Calculate the reluctance of the mass steel ring if a flux of 700 microwebers is produced on it. So you can see the material here is mass steel, right? So if we are to find the reluctance, so the formula for reluctance, is equals to what? The length of the magnetic flux path over the absolute permeability of the material times the area, right? Cross-sectional area. So with this formula, from the question, we are given the area is there. The length too is given 400 millimeters. Then we don't know the absolute permeability. So to get the absolute permeability, we know that absolute permeability of a material, in this case mass steel, is going to be equals what? Magnetic flux density over the magnetic field strength. So from this, in using the graph, we can calculate the magnetic flux density from what we are given here, because we know the area, and then we are asked to find the reluctance, right? Produce, meaning at a flux of 700 microwebers. So magnetic flux density, we know it's magnetic flux over area. That will be 700 micro over area, cross-sectional area 500 millimeters squared. That is 500 times 10 power minus 6. So this will cancel. We end up having 7 over, this will also cancel, 7 over 5, that is 1.4 Tesla. So we go and look for mass steel in the graph here. That is figure 1, right? Then we have mass steel. Then we trace 1.4 to get the corresponding, right? So we get here to what? 2,500. Right? Here 2,500. So the magnetic field strength here is 2,500. Write it here. 2,500, right? So for miles still, 2,500 amps per meter. Now with this, I can get in that case the absolute permeability by just dividing the magnetic flux density over the magnetic field strength. So the absolute permeability of mass steel here will be equals to 1.4 over 2,500. Okay. Now give me the answer for this to be equals to 1.4. So we get this answer for the what? Magnetic absolute permeability, which is 56 10 to the power 10 to the power 1, 1, 2, 3, 4, 6, right? 5600 power 6. Oh, yeah. 1, 2, 3, 4, 5. 5 rather. We have this. Okay. Now, we'll just this HOM. So we have this being the relative payment. Okay. So how do we move from there? Now I can go and get the what? From here, the reluctance, right? So I get the reluctance and I have what? The length, which is 400 over, now my absolute permeability is what? 5, 6 times h power minus 5 times the area. We already know the area to be 500 times this. 500 times h power minus 6. So we can see here, this you get 10 raised to the power minus 4, right? So this becomes, okay, let's cancel this with this. 400 with this. Now we just have 11, right? 10 raised to the power 10, 11. Then we have 56. So we just have 4 divided by 56 times 5. Right. So we end up having this times 10 raised to the power 11. Right. And that will be equals to, okay, we get a very big number. So the whole of this, when you do this, we get this answer. 142,8,571. Right. H inverse. So we can make this to be what? Kilo, right? So that we have 142 point, right? So let me put here point. So I can put the other ones as 0.57 kilo Henry inverse. So the answer here will be, or we can put here, the answer here will be C. Alright. Now, moving to the next question, which is 37. Calculate the current required to produce a flux of 700 microwebers in the ring. Now that we know the what? The reluctance, right? I know that, again, Fm is equals to, right, magnetic flux times reluctance. And Fm is also equals to Ni, right? So if I'm interested in the current will become equals to Fm, which is magnetic flux density times reluctance, magnetic flux rather times reluctance, then over what? Number of turns, right? So here we get here to be equals to the reluctance, which is just what? I can just use the answer here. 1429 kilo over what? The number of 10, 200, right? Over 200. And what do I get? In this, by 200. Right? Get this. Get this divided by. Oh, we have to multiply by the magnetic flux, right? This times magnetic flux. Oops. Times the magnetic flux, which is 700. 700 micro, right? So times this. So we have this times 700. Okay, so we have 1429. Right. So here this will cancel. We have here to be minus 3. And that would just be what? 0.7. So we have 1/4 times 0.7. 0.7. So we have 1000, right? The answer here 1000.3 all over 200. And that will give us 5. So the answer here is 8. You get 5. Now question preamble 4. And we are using preamble 4 to answer question 38 and 34. Right? 38 and 34. A uniform ring of cast steel has a cross-sectional area of 320.2 millimeters square and a mean circumference of 75 millimeters. A current of 0.40 amps flows in coil wound uniformly around the circuit, and the flux produces 300 micro Webers. The relative permeability of cast steel at this current value is 400. Find MMF needed to, question 38. Find MMF needed to produce the 300 micro, right? 300 micro Webers. Now with this, how do I find the FM? Again, thinking about the formulas that I can use. So with this, we can go through, right? We can use HL. We can use FM equals what? HL. And then with this, right? So I have to find magnetic field strength, which is H, and that will be equals, we know, that will be equals to what? We know that absolute permeability of what? The cast steel here is equals what? Magnetic flux density over the magnetic field strength, right? And that will give us, we make the magnetic field strength the subject, we get magnetic flux density over the what? Absolute permeability of cast steel, which is just what? permeability of free space times relative permeability of Castile, right? Now with this, we can even just write the whole formula. So we replace this and write here Fm, which is the mmf, will be equals to all of this times the length, right? So just bring the length here. And that will give us, yeah? We do replacement. Magnetic flux density is, so magnetic flux, we have to calculate that one, right? We know magnetic flux density is what? Magnetic flux over area. So I can even do replacement here too. So they will just flux times length, right? Over the absolute permeability times what? Area now. So we get this straightforward. So just do replacement. Magnetic flux is 300 milli. The length is what? The length is 75 millimeters. And then when it comes to the permeability of free space, that is 4 pi, that's 8 power minus 7 times what? Relative permeability of what? Castile is 400, right? 400. Then times the area. The area is giving us 3.2 times 8 power minus what? 6, right? Millimeters squared. So with all this, you solve this, you get the answer here to be equals to C, right? You get it to be 139.08 amps. Okay. Now, with this, we can calculate the number of turns, right? Because we know that Fm is equals to what? Current times the number of turns. So number of turns will be equals to Fm over current. And the current is given in the equation. It's given as 0.4. So we have 39.80 divided by 0.4. And what do we get? So we are going to get 39.808 divided by 0.4. Which is get 349.52. And since this is the number of 10, it has to be a whole number. So that will be what? We just change this. We round this off to get 350, right? 10. So that is question 39. We move on to question, right? Move on to question 40. So with question 40, the total flux in the core of an electrical machine is 20 milliwebers and its flux density is 0.8 Tesla. Calculate the cross-sectional area of the core. So we know that magnetic flux density, we are giving here, again, focus on what you are giving. We are giving the magnetic flux density. We are interested in the area. So we know that magnetic flux density is what? Magnetic flux over area. And area is going to be equals to what? Magnetic flux over magnetic flux density. So we have this being equals to magnetic flux 20 milli over the magnetic flux density, which is 0.8. So we have this, right? 8 is just 8. Is 0.8 is just what? 8 times 10 to the power minus 1. So that this and this, when this come here positive, so we have 10 to the power minus 2 here. 20 divided by 8. So we get 2.5. Right? So this will be equals to, right? So here you move to, that will be equals to 0.025 meters square. So I get the answer here to be D, right? Magnetic flux resistance is also called reluctance, right? When you talk about magnetic flux resistance, we are referring to a reluctance of a material. Because reluctance is the opposition to the establishment of magnetic flux in a material. Move on to question 42. If the total flux in a magnetic circuit is 2 milliwebers and the cross-sectional area of the circuit is 10 centimeters square, what will be the flux density of the material? Again, you can see we are given the flux and then this time area, the magnetic flux density, which is just what? Magnetic flux over area. That means I have 2 times 10 to the power minus 3 over area, 10 centimeters square, 10 times 10 to the power minus 4. So here, this will cancel one of these. We have 10 to the power minus 3. So this and this will cancel. We should have this equals 2 Tesla. So here the answer wasn't there. So this was given as bonus. Right? Bonus. Moving on to question 43. Question 42, we are using the figure, right? Figure 1, which is on page 11. A magnetic flux density of 0.7 Tesla is established on cast iron magnetic circuit. We are using this problem 5 to answer question 43 and 44. Now, we are to find the absolute permeability of the cast iron. Or here we are given the magnetic flux density of cast iron. So we have magnetic flux density cast iron, which is given as 0.75 Tesla. And we are interested in the absolute permeability of cast iron. We know that the absolute permeability of cast iron is going to be equals to the magnetic flux density over the magnetic field strength. So if we know the magnetic flux density of cast iron, which is given as 0.7, then we go and use a graph and get the corresponding magnetic field strength value, which is H. So the material here is cast iron. So you go to cast iron 0.7 Tesla. Cast iron. Cast iron. Yes, cast iron 0.7. 0.7. So we are here. So we trace down. That gives us 4,500. 4,500. 4,500. So we get this estimate 4,500. So this is of cast iron. 4,500 amps per meter. Then we get here to be 0.7 over 4,500. Right? We get this answer here. So what do I get? That would just be what? 7 times 10 to the power minus 1 over 4,500. So that here, 10 raised to the power 2, you bring it up, come negative. So 10 to the power minus 3. So 7 divided by 45. 7 divided by 45. So we have 0. 0. 1556, right? So milli. We get here to be 0.156 milli. So milli. So that will be what? C. The answer here is going to be C. Millihenry per meter. Determine the relative permeability of the cast iron. Relative, which we already did, right? Relative permeability of cast iron. That is... Okay, we have having so for that. This is the absolute permeability. That means I can just write here. We know the absolute permeability of cast iron. We know absolute permeability of cast iron is also equals to what? Permeability of free space and the relative permeability of cast iron. So this will just be equals to cast iron is going to be equals to permeability, absolute permeability of cast iron over permeability of free space. And that will be equals to, what we got here is 0.156 as h1 minus 3 all over 4 pi that's 8 power minus 7. And this will be equals to, you bring this up, 7, I would take this power 4. So we have 0.56 divided by 4 pi. Right, that would be what? 0. We get the answer 0.0121237. And just 1238. Right, we get this. That's 10 to the power 4. So that is just going to be in kilo. That was just 0.13 kilo. But we can move this. If you look at the possible answers here, 44. That is so here, right? So here move 4 times 1, 2, 3, 4. So the answer here will be what? D, right? Because 10 to the power 4 here. So we get the answer here to be D. Now question 45, right? Absolute permeability has no unit. This is false, right? It's as unit, right? So this will be false. The unit of absolute permeability is Henry per meter, which you can see here, right? You see the unit Henry per meter. And EMF, an EMF of 5 kilovolts is induced in the coil when a current of 5 amps collapses on uniformly to 0 in 10 milliseconds. Determine the induced inductance of the coil. So here we are interested in induced inductance. All right, so here we have 55 kilo. So we assume this is what the magnitude, right, of the induced EMF. So we have this formula, induced EMF in the coil with respect to what current, and then time we have induced what minus inductance and the rate of change of current over time, right? Now, if we have this, we are interested in inductance, so make inductance the subject, and here is positive, so I'll take the magnitude of this. That will just be this. right? Change of current over change of what? Time. So this will give us the formula will be this times change of time over divided by change of current. And here we do replacement. And what do we get? Inductance will be equals to the magnitude of EMF, which is 5 kilo, divided by, meaning times the time, right? 10 milli times 10⁻³ all over the current, which is 5. So we have it to be, this will cancel this, right? Time is 10 milli, right? So times 10. So here 10 here we will cancel out. So we just have 10. So we have 10 Henries, right? So the answer here is 10. Okay. Find the speed that a conductor of length 160 millimeters must be moved at right angles to a magnetic field of flux density 0.6 Tesla to induce in it an EMF of 1.8 volts. So this is question 45 that we are trying to solve. So again, focus on what we are given from the question. We are given the length, then the magnetic flux density, and then the induced EMF. We are interested in the velocity. When it comes to induced EMF or voltage in a conductor, we have this induced voltage equals to magnetic flux density times our velocity times the length, right? Because we have been told here, this is at right angle to the magnetic field, so you can use this formula. We make velocity the subject, we have induced voltage over magnetic flux density times length. And what do I get from this? Do replacement. The induced voltage is 1.8. Magnetic flux density of 0.6 times the length, which is 160 millimeters, right? Minus 3. And this will be 160. So the 0 here. Okay, we get 6 times 10 power minus 10. Minus 1. So this will go away with this. So I just have 1.8 over 6 times 16 times 10 power minus 3. From this, can get, you bring the 10 raised power minus 3 up 10 raised power 3. So I'll just have 1.8, right? We have here to be 1.8 divided by 6 times 1, 6. 6 times 6. Okay, we get 0.01875. So this is just times what? 1,000, right? So that would be 18.75. So the answer here will be B, right? Moving on to question 48. The energy loss due to hysteresis is greater for harder magnetic material than for softer magnetic material. The answer here is true, right? Because when you have what? A hard ferromagnetic material, it tends to have a large hysteresis loop. That is associated with what? A very huge loss of energy, right? conductor carries a current of 10 amps at right angles to a magnetic field having a flux density of 500 milli Tesla. If the length of the conductor in the field is 200 centimeters, the force on the conductor is. So we are interested in the force. Then we are given the current, the magnetic flux density, then the length. So we know force is equals to magnetic flux density times what? The current and the length of what? The conductor. And we have been told this is what? The magnetic field, right? Is at right angle to the conductor's right angle to the magnetic field. So we can use this formula here. Magnetic flux is 500 milli Tesla times current 10 times 200 centimeters. So I'm writing the 200 down here. Minus 2. So that's, we can do some this and this will just be 2. Then we have here this will cancel this. So we just have 10. So the answer here will be 10 newtons. The answer here is D. Okay. Moving on to the next question. We have question 50. When a current of 2 amps flows in the coil, the flux linking with the coil is 800 microwebers. If the coil inductance is 0.5 Henry, calculate the number of turns of the coil. So here, we're interested in the number of turns. Again, we are dealing with the coil, right? And then we are giving the number, right? We are giving the current, then the what? The magnetic flux, then we are also giving inductance. So here again is a formula that we are to use, right? To use a formula, the number of turns. So when it comes to this, how do I get this here? So we know inductance is equals to what? Number of turns times what? Flux over what? Current. So with this, we are making number of turns the subject. That will be equals to inductance times current over 1 magnetic flux. So inductance 0.5 times current 2 amps all over magnetic flux, which is 800 micro. So we have this here. Here with 5 times 10 to the power minus 1. So here we'll cancel here. This we have 10 to the power minus 4 here. You bring it up, you get 10 to the power 4 plus minus 1, 10 to the power minus 3. So now I just have what? 5 times 2, that will be 10. 10 divided by 8. 10 divided by 8. 1.25. So I have here 1.25 milli. Milli is the number of turns, right? So that's just 1.25. I mean, that will be 0.125. Okay. And here we rather 3, right? It's not positive. Positive 3. Because when this comes up, it's rather positive. So by looking at the answers, I even know that helped me to know that this is actually positive. So we have 1.25 times, meaning kilo, right? Kilo tens. Kilo tens. And kiloton will just be what? 12.5. Right? If you move this 3 times, it will be 1,250. So the answer here is B. So moving to question 51. Determine the mutual inductance between two coils when a current of 5 amps per second in one coil gives an EMF of 80 millivolts in the other. So here, this is what you're interested in, the mutual inductance. So this is for, again, this is a positive magnitude induced EMF, induced EMF. So we assume that is represent the magnitude. So when it comes to what two coils, the EMF induced in the second one, which is the other coil, will be minus mutual inductance times the change of current in the first coil. So here we take the magnitude of this so that we get this. This become positive, right? Then with this, we can now find out the mutual inductance by making it a subject. From this one, we are given the rate of change of current, right? Which is the whole of this. And that is what? 50 amps. So here, mutual inductance will just be equals to, meaning induced voltage over rate of change of current. And that will be equals to what? 80 millivolts over 50. So this will cancel. 8 divided by 5. 1.6. So we have 1.6 milli. So the answer here is C. Okay. Now, moving on to the next question. We have question 52. The direction of magnetic field is, thus, if the current flowing through the conductor is towards the viewer. We know that when it comes to current passing through a conductor, right? If the current is moving away from the conductor like this, moving away from the viewer, right? And you use a left hand grip rule, the current will be clockwise, right? We have clockwise direction. But now we have been told that if the current here is flowing what? Through the conductor and it's moving towards the viewer. So that means since it's moving toward, that will now be what? Anti-clockwise. It's the opposite, right? So here will be anti-clockwise. See? A relay depends. Question 53. A relay depends on that for its action. A permanent magnet, there are no, a hammer and a gun. A reversal of current is what? An electromagnet, right? If you have a relay, it rely on electromagnet. Once the electromagnet gets excited, it closes the contact, so you have a closed circuit. In question 54, in the hysteresis cycle, the value of magnetic field strength needed, which is H needed, to make the intensity of magnetization zero is called saturation. Intensity of magnetization here just means the magnetic flux density, right? Refers to magnetic flux density, right? So when it comes to the hysteresis cycle, the H needed, meaning the magnetic field needed to make the intensity of the magnetic flux density, in that case, the magnetic flux density zero, is called saturation point. No, this is not false. It is referred to as the cohesive force. So this is false. We call this cohesive force. right? Not saturation point. Determine the, question 55, determine the mutual inductance between two coils when a current changing at 50 amps in one coil induces an EMF of 90 millivolts in the other. So this repeated question, right? So here, okay, it's similar, right, to the other one we already saw. So here too is the same thing. We have mutual inductance equals to magnitude of the induced EMF over the rate of change of what? Current. So we have here to be 90 milli over 50. And this again cancel 9 divided by 5. That will be that is 1.8. So we have 1.8 milli Henry. So answer here is A. Okay. Question 56. A flux of 0.35 milliweb is passing through a 110 coil is reversed in 25 milliseconds. Find the magnitude of the EMF induced. So here we have been told this is in reverse. So to find the magnitude of the EMF induced, we can write the induced EMF formula for a coil. When it comes towards the magnetic flux and the time, mean the rate of change of magnetic flux, that will be minus number of turns times the rate of change of magnetic flux. And this is the magnitude. So if you take the magnitude of this, right, we should get a positive answer. So we have this. Now, when it comes to now, the number of turns is given as what? 130 times. We have been told the magnetic flux is reverse. So that means we have twice. We have the total. We can talk about the total change of magnetic flux. So that would be what? 0.35 times what? 2. Then divided by the time. And this happened within 25 milliseconds. 25 times 10 power minus 3. So what do I get here? So this is 35. 0.35 rather times 2 will just be 0.7. So I have here 130 times 0.7 over 25 times 10 power minus 3. So with this 0.7, you just 7 times 10 power minus 1. So this and this will cancel. So I have 13 times 7. So you bring this up, 10 to the power 3. So we have 17. No, we have 13 rather. 13 times 7. That will be -1. So we have -1 divided by 25. So 3.64. All right. We have 3.64. Yeah, this one is milli, right? I didn't bring, yeah, this one. The 0.35 is milli. So it will cancel with this. So the milli here will cancel with this one here. You just have what? Well, this one goes away. So we have 3.64. The answer is this one. Question 57. The ability of a material to keep its magnetized state when the magnetic field strength is 0 is called this retentivity, right? Refer to A, retentivity. In Fleming's left-hand rule, the thumb always represents, if you are using the thumb, that means that represents the motion, always represent the direction of magnetic field. This is false. The thumb represents the motion. So this is false. Which of the following materials would have a higher permeability, right? So yeah, any material that's going to have a high permeability, it means you can easily establish magnetic field on that particular material. So that would just be a ferromagnetic material. So you can see here glass is not even a magnetic material, so it's wrong. Paper, the same thing. Wood, so the answer here is cobalt. C. Then the last question, question 60. In the Fleming's left hand rule, the second finger always represents the direction of the current. So if you have Fleming's rule, the thumb represents the motion, direction of motion. First finger, the direction of magnetic field, and then the second finger indicates the direction of current. So the answer here is B, right? So we've come to the end of this section, right? We continue the next solution in the next video. Bye bye.